All right, so let's go ahead and begin class. So for this month, guys, it's really, it seems like a lot, but there's actually not as much as you might have originally anticipated. Um, Whoops, for this month, by the way, I'm starting to put my cover sheets on Google Docs now so I can easily update them and stuff. It won't matter so much for you guys. Actually, it might, if I make any like exclusions or something, I can make them on the fly, which is kind of nice.
Well, there's a print properly now.
Huh?
It's 3 pages, so 2.
Yeah, I'm super sorry.
I only printed 2.
Yeah, go ahead and just print like the one. In fact, you only need to print the one that actually, you just need to print the first one, I guess, because I don't ever have you sign or have your parents sign for this anymore. So here's the deal with this month. The only 2 sections that have truly new content would be 4.3 here, which we're going to go over today. We're going to start, and we're going to kind of skip ahead to, I think, the next biggest point. It's a bigger standard, I think, and that's L'Hopital's rule, okay? And I think that's not a bad concept at all compared to what you've already seen up to now. So I would say this 4.3 is a little unintuitive. It requires, I think, a little bit of a proof to kind of prove why we're doing things, right? 9.2, I think you'll kind of get the hang of pretty quick. And then hopefully in the third week or the second or third week, we can start going these things. 9.5, 6, and 7, it looks like it's part of a different book. It says something about Taylor. All that is like on the actual website under here, you'll actually see the month 7 Taylor packet. This is outside of your book. It's sections 9.5, 9.6, 9.7. So if you kind of look on the page numbers here, like where it says 9.5, like page 201, or like 204 or 207, they won't align with your textbook because you're not supposed to use your textbook, okay? So I use this packet that I kind of gave out, and this is what the packet's going to look like. This is what the packet's kind of look like here. And luckily, this time, too, if you go back on my website, there's actually an answer key to where you can check your answers. Not for all the questions. So my thing is whatever's on the cover sheet, like whatever's on the cover sheet here, like whatever I assign you guys, even if it doesn't completely align with the answers, I would say like you could skip ahead any that don't have any answers, and in place of any question that you skip, do a problem that does have an answer, okay?
So 1 for 1.
Yeah, 1 for 1, right? And if it still doesn't work out, let me know too, because I think some of these selections of questions that Ms. Carbajal picked previously in the years previous, I still think they're a little bit out of our depth of what we need to know sometimes. For some of us, I think you guys will look at it as a challenge and keep going. I encourage that. That's fine. But if you're not sure, come and see me, and I'll be able to identify, you probably won't see anything up to this level on the exam, or maybe you should work on this, okay? So again, really your only new content, your really truly new groundbreaking content is going to be 4.3 and 9.2. 9.5, 6, and 7 are extensions of things that we've seen before, just a little bit higher level stuff, okay, that you might see on the exam. And then after this month, it's just peer review. So this is pretty much the last month exam, okay? And then month 8 is just going to be all word problems. And just word, like FRQs, Yeah, and and there's a higher emphasis this time on the grading. I don't know if you guys saw, but I distributed the grading a little bit differently. It's still subject to change, but I put about 35% total in your homework. I know it says notes, but that's just a formality. We're not taking notes. So really, it's about 35% emphasis on the homework, 50% emphasis on the test, and 15% for test corrections. As of this point, I don't have like a project or anything because I'm still kind of running under the assumption that we're not going to do anything after the AP exam, okay? Unless I'm told otherwise, like.
Are we gonna still have classes though, or just literally just nothing?
No.
Good. As far as this class.
Yeah. As far as I know now, okay, I'll be honest, I haven't even checked with like the administrators yet, and that brings me to my next point. I haven't gone that far because I haven't even graded your exams yet, guys.
Good, because why would we keep going? These months, I feel like we're much harder than derivatives. So I can't have it go any harder.
Well, I think
Like, I'm gonna review this summer.
I think we capped the difficulty probably last month. But yeah, Aaron, did you have a question?
Yeah,
You may have already explained this, but the AP review packets, are those required to turn in, or are those just?
Nathan, just don't open your mouth.
Oh, hey guys. Yeah, they're part of the homework, but you know what? What I'll do is you can pick either or. Okay, you can just pick one. All right.
What was the question?
You missed it. No, I'm just kidding. No, I'm sorry. I'm just kidding, Ellie. I'm just kidding. I'm super kidding. That was really mean. I'm sorry. No. He just asked, hey, are those review packets on the cover sheet? Are they both due, or are they just like required assignments? I will say yes, but just choose between one or the other. Okay, but it's really to your benefit to do more, because remember, I always award you just to do a little bit extra credit or extra work on the side, and I award you some extra points for it. Because why not award you guys for a little bit more preparation on your own time, right? Or else you won't see a point to doing it. Yes.
So, you go first.
So 5, 4, and 7, 9.5. So for those,
So these three here?
we still have to do them, but they aren't as important for what we need to know.
I don't want to say that, but okay. I'll say this: 4.3 and 9.2 are definitely like huge standards we need to hit before I pretty much end like new content.
Okay.
And then 5, 6, and 7 are, I think, like, I mean, you can kind of see by the title, final integration techniques. They're like a little bit polishing up things you might see on the exam that we still want to go over, like types of different integration that we might have kind of skimmed over, we didn't really look at. But they're not like, they're like part of like a standard you've already hit before. We've already talked about integration, you know? We've talked about the big ideas in integration. Now we're just kind of looking over some things that maybe I think we should look at, like further extensions of integrations, you know? Whereas 4.3, so we're going to skip ahead again. So 4.3 and 9.2 is what I'm trying to hit today. Yeah. Okay, so we did 7.3, and I'm going to show you what the difference is a little bit. Like, we might have actually, but I want to go into this a little bit more in depth. And I feel like I look back at the section that we went over, like 7.3, that was like in month 4 for derivatives, inverse functions. And I don't recall going over the derivatives, inverse trig functions. And you'll kind of see what I'm talking about. Maybe you can
like the 1 over like x squared.
Yes, actually, yeah, it might be. It might be. By the way, anybody who did not get a handout, please come up and get it. And then question, Deja, did you have?
I kind of didn't really pay attention to the percentages last month. So what changed specifically? Like, what was it before?
It used to be a 75% emphasis on exams, 15%, 25% total on work, and then I think 5% on test corrections.
Oh, so you evened it out a little bit more.
A little bit more. I mean, I still put a heavy emphasis on the exam, you know, because it's just the math program's still rigorous here. Yeah, it's still like 50% of the class is still all work around it, and then like 50% is still the exams that you've taken up to this point. But you can really, I mean, I'm gonna try to prevent this, but I remember like a few students last year really like took advantage of like my incentivizing for every page of extra work you do, you boost your grade. I think that person went from like a B minus to like an A, so I think that's a high A too. So I don't think that reflects well on me as a teacher. So.
Well, did they do well on the AP test? I guess it's
Yeah, they did. Yeah, they did. So I guess it does kind of work itself out. All right, guys. Any other questions before I move on? Because now we got to hit some content here. Okay. So you are given a sheet right now of derivatives of inverse functions. Okay. There are the formulas. That's it.
4.3?
Yeah, this is for 4.3. Okay. This is for 4.3. Here's what I'm going to do for the warm-up. I'm going to launch you right into a question, and then you're going to utilize the formula based on what you just see and what you already know about derivatives and basically basic notation of derivatives. Okay. So let's kind of go backwards. We went over integration. Can you go forward? Okay, I'm not going to confuse you anymore. We've been doing integration this whole time. Can you do it the other way around and do derivatives now, right? So we're going back to derivatives. It's sort of like a time warp. here is going to be your problem. D of dx of inverse sine x squared. And that's it. I want you guys to give me the general derivative equation for inverse sine x squared given this formula sheet. What are we going to do? Okay? Good luck. It is up to you. It is. Oh, and I please ask you now. So, guys, everybody that's work. Or I mean, you guys can copy this down. Please work on the board. All right. I really want to emphasize back on the board work. All right. I really want you guys just to go for it. Just try and then fall a few times until you get it right. It'll be fun.
Mr. Weaver, the markers?
The markers.
Yeah.
Oh, there should be there's a bucket hiding behind there. Yeah. And if there's not enough markers, let me know. I got a few more. So again, please don't squeeze them, right? Don't like. I have some more over here. Does anybody need more dry erase pens? I have more over here. Yes.
Do you want us to leave it like this with the radical?
Yes, in this context, I'll be okay.
I don't like it. Why do you have to? It's like they taught us you can't keep right from the bottom.
Well, do you? I mean,
Now they're like, you can.
Oh, it's easy that way.
no, I can ask you to if you like. Like, we can do that.
No,
Like,
I mean like I'm fine with it.
oh, you're just saying like, why do that? Yeah. Well, it's a good habit to have. Just I hope it gets to the. I'm glad it's to the point where it's annoying. And now you know that like classical mathematicians like doing it because it becomes a habit. By the time you get to college, and let's say you do take math as a major, they'll look at you and be like, "Wow, like you've had the experience to where you've been annoyed by this and you've done it enough times to where it's annoying." Okay, that's good. I mean, don't show that you're annoyed by it. Just be like, "This is the correct way to do things," and the professor will be like, "Wow, that is a really great student." Okay. I had a lot of foreign professors get really mad at us for just being lazy and not doing that. So I don't know. Who knows? But it's usually those teachers from different countries that are much more rigorous, that have very, very beautiful mathematical and scientific skill and craft. It's quite a wonder to behold. Okay, so out of these 6 derivative functions or these derivative statements, which ones did you guys opt to use?
Arcsine.
Arcsine. How did you know it's arcsine?
Because it's our sign.
What is arcsine exactly?
The inverse of something?
Okay, so inverse sine is otherwise known as arcsine. Okay. And what did you guys define as your u?
X squared.
Okay. So in this case here, your u prime, the square root of 1 minus u squared. If your u is x squared, what is u prime going to be?
2x.
Very good. And then if you take u and you square it, so don't be misled, you have u is already x squared, then you have to take whatever u is, which is x squared. In this statement, you have to square it. Sorry, it's kind of hard to see there, but I'm squaring x squared. Your final statement is actually going to be 2x over the square root of 1 minus x to the 4th. Okay? And that should be your final answer, right?
Yeah.
Okay. All right. So let's go back on this really quick. Now, you look at these equations and you look at memorization, okay? I mean, it's a little bit unintuitive for what this is. Let's see if you talk about inverse derivatives, right? Let me see if I can kind of go back on this. Does anybody recall this statement here? The inverse function, if you take the derivative at some point A, or like, let's say there's a coordinate A comma B, okay, off to the side here. Let's kind of make this a separate note, right? The derivative of an inverse function is essentially 1 over the derivative at the point B. Does anybody recall that from 7-3? Doesn't have to be perfect, your recollection, but vaguely. This sounds sort of familiar, correct? Well, this is the difference between those two sections. In these two cases, we were just talking about any function and taking the inverse function of that function and then finding the derivative of that. That's what we did in 7.3. In this case today, we're only focusing on the inverse trig functions. That's the main difference. I think I still have a gut feeling that we've kind of skimmed over this before, but I wanted to go over this with a little bit more detail this time. Right? Now, this is still unintuitive. This doesn't look like anything, right? In fact, if we were to follow this, if I took, sine inverse of, let's say, just call this A, what should this theoretically be then? If I followed this formula here, what should have this been? What is it? Well, this is inverse sine. 1 over, it's not 1 over inverse sine. Cosine of B. But why is it that our paper down here says this odd statement here? U prime. I mean, there's a big fallacy in the way I wrote this too, because we're talking about in terms of A and B, and here I talk about in terms of U. But regardless, even if I switched around these letterings here, B, U, and U, it still doesn't quite look the same, but they are equivalent. Would you like to see a brief proof on why this is?
Yeah.
Okay. Ali's like, I beg to differ. No, I'll just take it at face value. I'm fine, which is fine. That was my learning too. Okay. Sorry to be so boring. Right? Okay, so this is actually ripped directly from your book, but I'm going to guide you along with a big step that they did not go over. Okay, so let's look at our function. Let's start with a general function. Y is equal to inverse sine of x. No biggie. The next few steps are not probably ways that you kind of approach inverse functions. Okay, when we kind of invert it the other way, like when we're talking about in terms of instead of y, we're going to talk about in terms of x. It might not be familiar ways with how you do it, but if you just follow along the steps and you just kind of go along with me and follow along the way the book kind of goes with this, it actually leads perfectly into the proof. Okay, so it is deliberate the way this was done. Okay, you'll kind of see what I mean, right? So here, if I wanted to find the inverse, if I wanted to find the inverse function relationship for this, then what I would do is I would have sine of y is equal to x. Okay. And the whole point of this was to find the derivative of the inverse function. So what I'm going to do is I'm going to find the derivative with respect to x. And whatever I do on one side, I got to do to the other side. And then here, I know it's a little bit difficult to kind of see and remember, but it's implicit differentiation. So if you remember to take the derivative of the outside function, this would be cosine of y with respect to the function y. the derivative of y times the derivative of y with respect to x. Is that? Yeah, go ahead. Yeah. And here, what is the derivative of x with respect to x? Sorry. Just 1. Now, remember, the whole point of this is to find the derivative of this inverse function, this inverse trig function. So what we're going to do is we're going to leave dy with respect to x on this left side, and then we're going to isolate that. So we're going to divide both sides by cosine of y. So now you have dy over dx is equal to 1 over cosine of y. And if you don't really recognize that now, what that's basically saying is the inverse function of, let's say, what was it? The inverse function of a, I'm sorry, not of a, but the derivative of the inverse function of a is equal to 1 over the derivative of the function with regards to b. It's hard to see, but what you see here is essentially this. Okay, this is what was done in 7-3. What you've learned in 7-3. Okay, yeah.
The second step, what happened to the inverses?
Oh,
Rest
I'm
of the
confused.
side.
here.
Yeah.
So we just manipulate to where instead of talking in terms of y, we now just shifted it over and put it in terms of x.
What
So
happened to the inverse?
here, it's sort of like if I took the sine, if I took this and I took the sine of inverse sine of x, like that. Sorry, that's inverse sine. If I took the sine of whatever the value of the inverse sine of x is, I would just get x.
Wait, then you just bring it to the other
Or
side.
you could like divide by
Yeah.
inverse sine, and then it would be like y divided by the inverse sine, and then you could just change it to sine of y.
Yeah.
Wait, you're telling me to divide
Well,
this
either way, you could think about it just divided
Uh-huh.
by inverse sine, and then
We were just taught that you just bring it to the other side and it's no longer inverse.
yeah, but you can't really
no, because
divide it by
then it would be y divided by inverse sine.
yeah.
Then can't you just change it to
Sine.
sine times y?
Yeah.
Or sine of y.
The thing is, you can't. The sign isn't a value to multiply by. That's not. Yeah. It's not necessarily.
You said it's not to be multiplied by, but he said that you times it by y.
Oh, I times it by
You
y.
times it by y.
Never mind.
Yeah, it's not quite that. It's like it's a function in itself, but there's no inherent value in sine. So
You can always bring it to the other side.
you can, but it's not quite conceptually what you're thinking.
Can you just write out all the steps of how you got from 1 to 2?
Okay, so do you want me to? Okay, so let me show you.
Sorry.
No, it's fine. It's fine. It's fine. So here's how I did it. Right? Maybe it helps if I took a pen here. If I took a different colored pen. Okay. So little side step here, right? I have y is equal to inverse sine of x, correct? What I do now is I take the sine of this. And then what that will do is if I take the sine of the inverse sine of x, then I will just get x. Yeah.
Oh, it all makes sense now.
But just to let you,
So you multiply both sides by sine.
just
Correct.
so that's the thing. Don't get it confused with that. I know it's hard to see that because I would think the same thing, that it looks like you're just multiplying it, but it's like you're taking the sine of something, right? It's like, how can I conceptualize this a little bit better?
Oh, so you didn't multiply both sides.
It's like pretend like this meant that it's taking the reciprocal of x. Can you multiply the idea of a reciprocal? Do you see what I'm saying? Like if I said, what if sine was a way of saying take the reciprocal of x, right? And I took the reciprocal and I said sine is take the reciprocal of the reciprocal of x. I would just get x again, right? But the fact that I'm asking you to take the reciprocal doesn't mean I'm multiplying it to the idea of taking the reciprocal. Does that make sense?
No, because if you have 1/2 and you take the reciprocal and multiply it, that's 2 and that's 1, which is what you just did. But you multiplied it by that.
Okay, so maybe that's
I
not.
think I actually maybe able to kind of explain.
Go ahead.
So,
Yes.
Did I make sense though? Because that's what I was thinking.
Yeah, and I realized my example might have been not a great example. So
So in this particular case, y is equal to the inverse sine of x. So if you could see that as, for instance, y is 3, so it would be equal to 3 is equal to itself. So both are 3. So if you'd be taking the sine of both sides, it'd still be the same number. So if again you replace 3 with y or sine of -1, it would be then sine of y equals to sine of the inverse sine. So it's not multiplication, it's still equal, just taking the sine of both sides. It works.
Ben had a moment.
Well,
Go ahead, Ben. This is great. Yeah,
so,
I like this. This is good.
well, there's a difference between like taking. So let's say that you. So this means something different than if you did sine of x times sine minus 1 of x. Because in this one you're taking the sine of the inverse sine.
It's like sine
But
inverse.
for this one you're multiplying the sine by the inverse sine. They're like different things.
They are.
Yeah, you do what's in
Yeah.
the parentheses and then you multiply it, right? Is that what you're
It's
saying?
not, this one is multiplication. So this one would be composition. You take one function and then you take another function.
No, I get it. That makes sense when you say it that way.
Ben, that was beautifully done, Ben. Yeah, congratulations. That was awesome. Yeah, no, applaud.
Yeah.
Applaud, guys. Young Ben, thank you, Ben. Yeah. All right, so if I'll add a little bit to this. This has a value now, a sine of some number, right?
Yeah.
If you put that into the calculator, right? Maybe make sense of this. Can you put just sine, S-I-N, and then press enter, and it'll give you an actual value?
Oh, that makes sense.
Does that make
The
sense?
error.
Yeah. So it would just give you error because what it does is it does things with the number. So you're not really multiplying that function because it doesn't actually have a value unless you attach an x inside of it. Okay.
Okay.
So
Thank you.
that's what's happening here. So that's the clarification I want to make there. Okay. So don't and you might not even meant that, Christina, too. You might have just said, I just didn't know the words for it. So I just said I multiplied mystery, but I know. Okay. So I'm sorry. That might be the case too. So just to kind of clarify some language, I guess. Don't ever say you multiply by sine, but you take the sine of something. Okay? Yeah, it's a function. That's it. So anyways, that's what happened there. So does that make sense now, Deja, too, with this clarification?
Yes, thank you.
Okay. So not to confuse you here. So I have this going on here, and we're not done. Okay. So if you can kind of see here, y was a inverse function, right? I took the derivative of y, which was an inverse function. Okay. And that is 1 over cosine of, y. I started with my independent variable being x, and now I have the independent variable being y. Sort of like the way this is written. If you look very closely, these are saying almost the same thing. The derivative of the inverse function. Again, the inverse function was the inverse sine of x, right? The derivative of this guy, right, which is dy over dx, is these two right here. Okay, is 1 over the derivative of the function of just sine, which was cosine of y. Again, 1 over the derivative of just the function, not the inverse function, but just the function. And then of the other term, b. In this case, we have y instead of x. Does that sort of make sense? Okay. if it doesn't, I'm going to post this up. So just rewind it a few times, okay? And then until it kind of makes a little bit of sense, okay? But the question is, where does this become this form here? Something that looks sort of like what we have on our cheat sheet. That's the question. I don't know, okay? So we're going to answer that. That's why I'm going to write this out. And say, no. It's not a question anymore. We're going to answer this question now. Okay? Here is the big leap in your book that it does not properly describe. Okay? This is a very, very, very big leap. What happens here is they replace this with 1 over the square root of 1 minus sine y squared. I'm going to write that a little bit bigger so it's a little bit more clear. Again, they rewrite this whole thing into this. 1 over the square root of 1 minus sine y squared. Does anybody know how on earth we got to that statement? Yeah, go ahead.
There's like an identity.
Yeah, I don't see where the square root came from.
So,
Because cosine squared plus x is equal to what?
slow down. Say it very slowly for Mr. Wade to catch up.
Cosine squared plus x is equal to what? You square root.
So it's,
Just
say it again, cosine squared y, sine squared y.
And then you solve for cosine.
So cosine squared.
Okay, so we have this trigonometric property.
So then you subtract by sine squared. So cosine squared.
Okay, so we subtract by
equals
sine y
1
squared.
minus sine squared, and then you have to take the square root of that, and then the square root of 1 is just 1, and then keep the sine squared.
All right, I'm just following on with exactly what you're telling me to do. So,
Square root.
and then we have to take the square root. Okay, so now we're left with y is equal. Oh, sorry, cosine y is now equal to the square root of 1 minus sine squared of y.
How do you get the 1 over it? There's no 1 over it.
Oh, because here, remember, it was 1 over cosine of y. So now we just take, so the only thing that we were looking at is this guy here, Deja. This is cosine y. Then we did all this work to find what cosine of y is equal to. Yeah, and then now we stick this guy, this bugger, back in the bottom here, right? Okay, still doesn't look like what we like though, what we want. Okay, not gonna help. So here's where it looks like circular logic, right? Like as if a child made this, like, oh well, I'll still make it work. Okay, you go back, and what they did was, all right, well, I'm not finished. That y right there, I'm gonna go all the way back to the beginning and plug in what I originally had. Y is equal to sine inverse sine of x to put everything back in terms of x. Okay, so you're going to have this 1 divided by the square root of 1 minus sine, prepare yourselves, okay? Sine of, now instead of saying just, I am so sorry, right there. Okay, so instead of saying just y right here, I'm going to replace that whole y statement with what y was originally equal to since the beginning. Y is originally equal to inverse sine of x. So here's what it's going to look like. Inverse sine of x. And don't forget, we're squaring this whole statement. So don't be scared. Hold on, let's take this step by step. It's going to be 1 over, what is sine of inverse sine of x? Let's take it step by step. What is sine of?
It just cancels out.
It's just x. And then we square that, leaving us with 1 divided by square root of 1 minus x squared. And ta-da, that's what we have. dy is equal over dx is equal to this. And there we are. That is the derivative of arc sine, okay? So if we had to put it in terms of u, however, so let's go back. Let's say if we took the derivative of, again, what we just did was if we took the derivative of the inverse sine, now let's just say instead of x, maybe it's not necessarily x, but it's something that could be a chain rule. There's something inside in the parentheses that could have been you could have taken the derivative of even further. So to make this a more comprehensive, more robust formula, okay, is if we had this, it would be the same thing, 1 over 1 minus u squared now. But let's say if u was differentiable, then you could say it'd be times du over dx. And you're like, wait, what? It's the same thing as saying this, 1 over the square root of 1 minus u squared times u prime. Okay, think of this as being u prime. And then if you look back on your cheat sheet, that's exactly what you have now. You have u prime divided by 1 minus u squared. Okay. If there's any steps that you might have been lost in, I would recommend to go back on this video that I'll post up tonight. Okay. But I think for the most part, you guys are pretty good. Do you guys want to do the proofs for the other ones? I was kidding. Okay, we're not going to do that. But you understand sort of the idea and the methodology for where this comes from. No. They're pretty intuitive as well.
Actually, especially cosine, basically for the cosine, the derivative of cosine is just going to be negative sign, so that's where the negative.
Oh, did you take a look at this here?
Oh.
Did you guys see that? Yeah, if you guys take a look at all of them, they're all pretty similar. But namely, if you have sine and cosine, it's just the derivative of what we have here. Well, we have this already, and you just take the negative of that. If you don't, that doesn't sit well with you with what Aaron just said. There's a little cheap way to do that. Here are more trigonometric identities. You can think of it this way. Another trigonometric identity you might not know is that inverse sine or inverse cosine of x is also equal to pi over 2 minus, pay attention, minus inverse sine of x. If I took the derivative of this guy, right, and I took the derivative of both sides, basically, what is the derivative of pi over 2? A constant.
0.
It's 0 minus whatever the derivative of this guy is. What is the derivative of that guy? Hint, hint. Nope. It's what we just did. So it would be 0 minus u prime over square root of 1 minus u squared. And ta-da, if you pay attention, that is exactly what we have right here. Okay? So there's two ways to make sense of it, right? Okay, so there are inverse functions and inverse cofunctions, okay? Or derivatives of those, right? So now let's move on to more sample problems, shall we? No, I'm bumbling around. Okay. So I'm impressed. You guys are really naturally fascinated in this stuff. And you guys are really naturally pretty quick at this stuff. Yes? I would say we're gonna try to get to 9.5. Well, 9.5 actually has to deal with this a lot, but we're not gonna touch that, like the Taylor packet, until the third week. I want to get through L'Hopital's rule, which is a 9-2, and then this section, inverse derivatives. Okay. Yeah, inverse trig function derivatives. Okay. All right, you guys want a challenging one? Yeah. All right, cool. Great. Okay. Okay. All right. Where I'm just gonna throw you in the deep end. I like that. That's too funny. Okay.
Why are we doing this in terms of S? Why not?
It's completely arbitrary, my friend.
I'm not. I'm just going to do S.
All right, there you are. There is your problem. Use your cheat sheet. Okay. You may use your cheat sheet. Yes, please. On the board. All right. L'Hopital's rule.
Can we be over there?
Yeah, go ahead. Any whiteboard you see over there, go ahead and grab them. It's your playground. Okay. Don't write on the walls, but just right on chalkboard. Yeah, you guys are okay to tell that to me. That's fine. My 8th graders, they're little nuts. So be very careful with this one because there's an absolute value there. It doesn't make things that much more difficult. It just throws you for a loop. You guys already finished with yours?
Yeah.
Let me. It is. Did you want a really hard one then? I have one if you really want to do it.
I'll try it.
Okay.
I'll take the challenge.
All right. Here you are. Are you ready? All right. So let's see. Number 5.
But I'm not getting up on the board though.
All right. That's the one. Oh yeah. This is a good doozy one. This is just very tedious. Yep.
Do you have to keep it with absolute values? Because sometimes when I work a problem like this, and they just kept it with parentheses, and they didn't have absolute values.
No. I would prefer your final answer.
Well, if it's something like, sometimes if it's something like x absolute value of x squared is always positive. So you can just get rid of the.
Oh,
value.
it was something like that. Okay.
I wouldn't have been able to answer that. Wow, this is good. Thank you, Ben. Yeah, you saved me. Yeah. Sure. Yeah. That's right, Ben. That's right. That's very, very good, Ben. All right, so let me first write out the solution for this. So, let's see. Yeah? No, I didn't. Why do you ask? Huh? Oh, no. I could do this. No, it's not that. Yeah, it was really cool. Yeah. But, I was working with some 8th grade stuff, too. So.
Do you usually go up to school?
Oh, that's true.
I'm sorry, what?
Do you usually go to school?
Yeah, because I have the proper gear to kind of get through the cold. So, and it's really good because there's no crowd too as well. All right, so this is what you should have gone here. What is it? It's S. What did I get? Oh, it's S. It is S. Okay. All right, just making sure. I didn't know if I wrote a 5 or an S there. Okay. All right, so this should have been your final answer here. All right, so you guys should have used, I'm not going to go through the steps, but you should have used this formula over here. Let me give you a challenge problem, but you don't have to do it. Do you want to do it? You want? It's fine. The challenge problem is this. I don't know if we should do this in class, but yeah, why not? I'll give you guys like 5 minutes to do this one. I think this one's.
There's a lot of steps to it.
Challenge it.
Yeah.
Credit.
It's just a lot of simplifications. Did you want me to go through the steps?
No. Oh. It shouldn't be X. No.
Did you want me to go through the steps here? I'm sorry.
How can you, I'm just confused where you got x squared plus x.
Okay, so
Oh yeah, I did. Yeah.
well, let me see.
You evaluated, took it out.
The square root of 4 equals 2.
So let me go through the steps. Hold on. So we're backing up really quick just to kind of go through that problem. Y prime is equal to u prime over the absolute value of u times the square root of u squared plus 1. What are we defining as u?
2x plus 1. Oh, 2s.
2s plus 1. Now we're going to plug this back into wherever the positions of u are. So what is u prime, by the way?
2.
So I like to kind of do the stuff on the side here. U prime is equal to 2. And how about u squared? What do we have to do for u squared?
2s plus 1 parentheses 2s plus 1
Oh, did you go
and
through?
then do the FOIL
Mm-hmm.
first.
So it'd be 2s, 2s
So,
before s squared.
Oh, so you guys actually did that whole thing. I just left it.
Yeah, so
Because why?
That was really mean.
Because then you wouldn't, how would you know to distribute the 4 out?
Well, okay, so if it's on the AP exam and you have like a multiple choice and that doesn't pop up, then you can distribute. But if that's your answer and you see that answer,
You're assuming that it's
multiple
multiple choice when there's no.
it is. Well, if it isn't multiple choice, then you can leave it that way. Because they're not going to take away points for not
Oh, I see
simplifying.
what you're saying.
Simplification is not required unless it's for multiple choice, in which case you
Oh, I
have
see
to
what
match
you're
up with one of them.
Which might be worth it to
Wait,
kind of
so
go
if
through
it's
and see.
Are you sure they won't think like, ooh, that's sloppy?
No.
You're so funny. You guys are
I mean,
ridiculous.
unless it's not legible.
How did you take a 2 out of it?
Okay, so let's see. Yeah, let's kind of back up for a second. So we have, what is it? We have 4s squared. Am I doing something wrong here? Let's see. 1 plus 1. That's right. Okay, so we have.
fourth word.
Oh wait, hold on.
What I don't understand is why
Yeah,
did you
No. Yeah.
Minus 1 is 2.
Thank you so much,
I'm gonna
Omar.
put something that I don't understand.
So back up a second. Our formula is u squared minus 1. So I was incorrect in doing this. So it's 4s squared plus 4s plus 1. That is in place of u squared minus 1. Okay. So now if we had to rewrite this, it would be the 2 over the absolute value of 2s plus 1. And then you're going to have positive 1, negative 1, or minus 1 are going to cancel out, giving us 4s squared plus 4s. You might be already able to see where I'm going to go with this. I could factor out technically 4s out of both of these, but I'll tell you right now that that's not really going to be useful. Just factor out 4 for both of these.
Well, you take out 4 and then you can take
Mr. Weeks,
2
you
out
do
of the
this.
square root.
Yes, that's
And then
correct.
you cross out the 2.
So you have
That's how you got your answer.
So you have 4 times s squared plus s, and then you can take out the 4, or you can take the square root of 4, which is just 2. So it'd be 2 over 2s plus 1. And then you pull out the 4 out of the square root. It is now 2 times the square root of s squared plus s. Please note that this term, this expression, and this expression all be multiplied to each other, making the 2 and the 2 viable to cancel out. So now you have 1 over, I'm so sorry about that, the absolute value of 2s plus 1 times the square root of s squared plus s. That is your final simplified answer. Okay? So that's actually really good, especially for the purposes of this video instead of just giving you guys the answer. Okay, so no time for the challenge problem then.
So just to
Huh? No.
just to be honest,
No, that's good. That's a good drive.
Why is the car bigger than the house? Okay, start away.
well, this
But that means the car is bigger.
Suspected Christina.
All right. We are now on to 9-2. So we are jumping around. This is a prepare yourselves. It looks like it's spelled La Hospitals, okay? But it's La
You
Hopitals.
don't pronounce an H in
L'Hôpitals. L'Hôpitals rule. Are you? Oh. You are genuinely excited about this. I'm happy. I'm very happy to hear. Okay.
I read about this in like month 1. I was like, whoa.
Wow.
Whoa.
Yeah, you are way.
I read about this in
That is awesome,
seven.
Aaron. I love it.
I read about this in month 5.
I haven't heard it until
It's
now.
awesome.
I know, Sam.
Okay, so can anyone tell me what the problem is if I take the limit as x approaches 2 of this statement here? In fact, let's go back to limits.
0 over 0.
How did you get 0 over 0, by the way, as the
I
limit?
just assumed because this is L'Hôpital.
It could have been infinity over infinity.
Hold on.
It is.
But it's not like a number.
Hold on, guys. Let's back up a second. Where exactly is Aaron getting these numbers 0 over 0? What did he do?
She plugged it in.
He plugged in 2, right? First thing when we take limits, let's review, backtrack. You always just try to see if you can just plug it in, okay? It's sometimes amusingly funny to see how people like really throw themselves overboard on a multiple choice problem when all they could have done is just plugged it in. And they probably like L'Hopital's rule was like, I'm not getting the answer. It's like you could have just plugged it in. Just try that. Always just try that. It never hurts to try it. So if you did 5 times 2 squared minus 3 times 2 minus 14 over 2 squared plus 2 minus 6. On the bottom, you should recognize that that's 4 plus 2 minus 6. That is 0. And then 5 times 4, so it's 2 squared, that's 4, that's 20 minus 6. That's 14 minus 14, that is 0. In fact, guys, yes, this is nothing, actually. This isn't, well, a more appropriate way to say this is not nothing, it's just indeterminate, okay? It's not a number that is divided by 0, because what would that lead us to? What? Yeah, it wouldn't be undefined, but what do we know that as?
Does not exist.
You know, if it's the other way, if it was 0 divided by 3, it would be 0. But if it's 0 is on the bottom, it's undefined.
Well, it's undefined, but what do we know that as on the graph?
Does not exist.
Infinity.
Does not know.
Yeah, it does not exist, but it goes off into infinity, right? As an asymptote. 0 divided by 0, however, doesn't tell us anything. If you tried graphing that, that won't give you an asymptote. It won't give you anything. What we call this is it's almost like a level different. I'm not gonna say above or beyond or below. I'm gonna say it's indeterminate.
Because I think it's like you're trying to figure out how many zeros are in 0, and you want to say 1 because it's like 1 0 and 0.
Yeah, conceptually, does that even make sense? How many zeros are in 0? 0. What? Like, it's just an indeterminate number. There's no sense to it. Okay. Let me give you a list of other things you cannot have. You cannot have an indeterminate answer. What that means in the world of math is you need to do a little bit more math to get a real number because that's not going to suffice, okay? You can never have 0 divided by 0. You can have 3 divided by 0. You could have 0 divided by 3, but you cannot have 0 divided by 0, okay? I know that sounds ridiculous, but there are some rules here, all right? There are some ground rules. Here are things that I consider indeterminate that don't make me personally mad, okay? But it's mad to me, right? To the fact that we don't know what's called. We just call it indeterminate. I don't know what this is. I can't make heads or tails of this. If you have a statement that is infinity or infinity, you need to do more math. You are indeterminate. That is not good. Let me see. What else? If you have 0 to the 0 power, what? You are indeterminate, right? No idea what you're saying. If you have 1 to the infinity power, okay, go home, right? You are out there. I don't know what's going on. If you are infinity to the 0 power, you are indeterminate. Okay, wow, does this make sense? 0 times infinity, okay, right? Fine. And infinity minus infinity. I get what you're saying, but no, okay? So we have 7 different forms. No one does.
Wait, but you get what they're saying. That's just 0.
You would think so, but where exactly does your boundaries of infinity start and end? But there is no end.
There is no end.
We don't know.
Values of infinity.
It's just indeterminate, okay?
Is it anything like minus itself or whatever?
It just doesn't make sense, right? Do you see how? Just think of it this way. The state of chaos that we're thrown into right now in discussing this is indeterminate. Think of that, okay? If you and I cannot settle upon a well-agreed answer and we keep debating about it, like as if like what came first, the chicken or the egg, consider it indeterminate, okay? There we are. Don't.
It did.
I don't know.
No, the chicken probably came from something else.
Do you see what happens when you talk about indeterminate terms? It's not worth the time, Nathan. Okay, so does anybody have a suggestion for what we can do to find a proper limit? Yes.
You take the derivative of the numerator and the denominator.
Whoa. Yeah, you could. Yeah. Yes. But I was gonna go for something a lot easier.
It's a polynomial.
This is L'Hopital.
Well, okay, yes, you could do that, or this was just a warm up, so you didn't actually need to do L'Hopital's rule, but give me a second. Give me 1 second. All right, if you
I do know the rule.
I thought that was the rule.
Okay, if you are able to factor these out into two binomials, it does factor out to 5x plus 7 times x minus 2. I know this isn't L'Hopital's rule, okay? X plus 3 times x minus 2, okay? This is the way that we've been doing this before. We would sort of factor them, we would try to cancel things out, and then we would try to get left with something where we could plug in x is equal, or x approaches 2 into this here. Will that give us a indeterminate form anymore? So what would this be then if we plugged in 2? Okay, so if you can imagine, okay, on the graph here, if I plug this into Desmos, which I don't have time to do, if I plug this, actually I do, I lied. If I go into Desmos right now, what will we expect to see for this at x equals 2? What do we, any hypotheses on what we should expect to see if I plug in the whole equation? 5x squared
The whole equation without factoring anything.
without any factoring. It has to
It'll
include.
be like, can't do this. I know.
It'll just be like straight. Like a line.
Yeah, it'll have to have.
So what's the limit though as x approaches 2?
Hey, what's up?
Okay, where is x approaching 2? Let's see, did I write that
Would it be
correctly?
a hole? Yeah. There'd be a hole at x equals 2.
It just says at the time.
It is undefined, but do we see where it's sort of approaching? What is 17 divided by 5? Someone do that really quick in their calculator. 3.4. So where does it look like it's approaching about? It approaches 3.4, but does it ever actually hit 3.4?
No, but we don't care if it's a limit.
Yes, that's right. We're seeing where it approaches. The limit is. But it doesn't necessarily mean. So again, just to reiterate, really good review, limit does not necessarily mean what the function equals at that point. It just tells you where it's going to, okay? We all know it's going to about 3.4, but we know that if we actually plugged in 2, it actually give us a number that is not just undefined, but indeterminate. Again, if this was some number divided by 0, this would be an asymptote. It would go to infinity, right? If it was 0 divided by a number, then what would we get? What is 0 divided by any number? 0. Then we should see 0. But again, this is indeterminate, so we don't see an asymptote or 0. We get this weird non-existent number off our plane of his existence. Okay? Does that sort of make sense? That's why this is indeterminate. We just don't know what to say about this thing. Okay?
Do you ever use like those numbers? Like imaginary numbers and whatnot?
Not in terms of what I know, in terms of my math. I'm limited in terms of any application to those values. Kind of seems scary too, conceptually. Yeah, it sounds almost like science fiction, but maybe at some point when you take enough math, you're like, wow, Mr. B, that was actually very tangible. But I don't know it in terms of my scope of knowledge, okay? The thing is, you guys have already seemed to know what L'Hopital's rule is. You guys already ruined the surprise. No, I'm just kidding. I'm very happy you guys.
Because you had a month
I
where,
still
the reason
don't
why I
get
know
it.
that is because you had a month where one of the problems was like this, and it didn't occur to me to factor it out.
And you
So I was
actually, you
Yeah.
learned it that way. That's correct. That was correct.
You
So
put something that was hard, too hard. You always do
I put you in that bind. I'm so sorry about that. Okay. Well, what is the problem with, we didn't really go over it, but what is the problem with this method that I went over?
It
that-
won't always work.
It won't always work. What do you mean it won't always
Like, you can't always be for certain that you'll have a polynomial that will both have a factor in the numerator and the denominator and cancel
But
out.
that gives you the
Yeah.
Yeah, it won't always be a polynomial, like it could be sine of x and you can't factor that.
I don't know about that. Let me see. Let me see, Ben.
Like if it was sine of x over, like if it was sine of x over x.
I don't want to do that, Ben. All right, hold on.
You can't factor.
What about this, Ben? Could I? What about that? Yes. Could you? No, you can't do a polynomial. So what is so if I took the limit of this? Sorry, Ben. This isn't disproving you at all. I don't know where I was going with it. Okay, it just kind of goes, huh?
Are we solving this?
No, we're not. No, we're not. Okay, let's just go with assuming we don't know what L'Hopital's rule is, guys. Okay, I'm just kidding. Right? Could you factor any of these things out into any other factors that we could cancel out? All right, let's do that. Okay, so let's do the limit as x approaches 0.
Should we make the face? Should we make the face?
I'm not a show monkey. Okay. Okay. So does that help us though? What if I plugged in 0 now?
There's still an x on the bottom. You have to get rid of that x.
Okay, so you would get the limit, and then that'd be 2 times e to 3 times 0 minus 1.
This sounds stupid, but I thought like a number to the 0 power equals 1.
It is.
Oh, okay.
But I think oh no, yeah, but what you're asking here is ridiculous though. This and this just don't make any sense. Okay, so you're right.
Why is it infinity to the power 0, 1?
Zero.
I can't answer. I have no idea. Yeah. You really stumped me. So, yeah. That's why it's indeterminate. Yeah, I don't know.
I was like this whole time since you put that up, I was thinking that in my head, and I was like, I don't want to say it. I don't want to be the dumb kid.
All right, so hold on. I still continue down this rabbit hole. Okay, and then we have 2 times 1 minus 1, which is 2 times 0 divided by 0, which is 0 divided by 0.
So it's going to be 0 because there's an x on the bottom.
Because there's an x. So Christina's already found out. Okay. I don't
The
know.
only way to
crazy.
solve it is to get rid of the x on the bottom, but we can't really do that.
I think 0.
Now you can.
I think 0.
As if
0 equals
no one knew here, right? Okay. All right. Let's go over what L'Hopital's rule is. You guys ready? This is a very, very beautiful technique.
Oh yeah, Captain.
I just say L'Hopital because it's easier.
Let's get the s.
That's the N word.
Can anybody read that? L'Hopital's
Oh,
rule?
but you can swallow it. Or sorry,
What?
I don't know how to say this in English. I didn't say this in English, but in Russian you say swallow a letter. It means just to not pronounce it, I guess.
Oh, got you.
Sorry, it's just swallow.
I was very educated. I don't know. Yeah. I don't know.
Sorry.
No,
Russian,
seriously,
you can
in
just write
French,
letters.
the H is silent. That's why there's the H.
I
in there.
everybody just tells me to swallow. Like, whoa, okay, let's calm down now.
All right. So here's the definition of L'Hopital's rule. If the limit has 2 terms in such a way that they're almost differentiable equations stacked on top of each other, right? Like almost like there's a differentiable equation in the numerator as well as a separate differentiable equation or expression in the denominator as x approaches, let me see, c, some number c, okay? We're talking about a limit now. And it produces, oh, I'm sorry. Let's say it's if the limit as x approaches c produces, I'm sorry, so bad English here, produces an indeterminate form, back up here for a second, indeterminate form, then the limit as x approaches c of f of x over g of x, or an expression that is differentiable, can be separated as a differentiable expression on the top as well as a separate differentiable function on the bottom, then what you can do is this. The limit as x approaches c, you can take the derivative of the top separately, completely separately, and divide it by the derivative of the expression on the bottom. Again, you derive the numerator and denominator separately, comma, not as a quotient. So don't think back to the quotient rule, okay? Don't treat it as that. Just for the purposes of trying to find the limit, where the limit gives you an indeterminate form, you can take the derivative separately of a numerator and a denominator. If you could separate your whole function into two expressions that have a differentiable expression on the numerator and a differentiable expression on the denominator. So let's go back really quick to our previous example. Here, instead of trying to factor out a polynomial, because that's not actually easy, I went straight from 5x squared minus 3x minus 14, and I just somehow did this in my head, 5x plus 7 times 5x minus 2. That might not be the most efficient way to solve this problem. So if I were to go back and resolve for this using L'Hopital's rule, right?
Isn't that what Deja said at the beginning? Just to see the derivative?
That's exactly what she said. And that's exactly...
No.
No, it's not that, Christina. I think you're just a very good sport. And you're like, I'll just go along with what Mr. Ruiz says, right? But the truth is, yeah, I exile these two for the time being. Just for like a temporary second. Like, how could you know these things ahead of me? Okay. All right. So let's take the derivative of the top. What is 5x squared minus 3x minus 14? What is the derivative of that statement? We're still taking the 10x minus 3 over 2x plus 1. You're excited about it too. I did go ahead. Breaking every religion I can. Yeah. Okay. So it's 10 times. So now we have a statement where, let's see if we can plug in 2 directly into this. It's 10 times 2 minus 3 over 2 times 2 plus 1.
Look at that. 17 over 5.
That's what Allie said. Good job, Allie.
17 over 5. Isn't that a much faster way to solve for these limits that give you indeterminate forms? Yes? It depends, depending on the context, correct? Right? No, it's not. You are in full. You just jump ship. This is the way to go, Mr. Lee. There's no other way.
Well, okay, for a limit that isn't 0 over 0 and infinity over infinity, then yes, it would be just a lot easier to do it like a regular.
All right, so now here is your new problem. Going back to my example, I had no idea what I was trying to do with Ben, okay?
We're doing this now?
Yes, now please solve for this limit.
6.
On the board.
Okay.
What?
I'm just gonna do it.
I'm just going to do it in my papers. Forget this.
I'm a little thirsty.
Careful.
Why'd you leave it? Why'd you leave it? Why did you not take
I just walked away after that.
take it down to minus what?
Is that X?
No, this is E. This is E. Remember, derivatives of E are the same. So it's just obvious.
I thought it was 3 and then the E.
And then you do
So you put. So it's just chain rule. So the
Isn't it 3?
of the E to the 3x on its own is E to the 3x, and then you can bring out
I was.
what?
Very nice.
No,
Not
but
the
the
whole thing. It's
3.
just chain rule. Just the derivative of the next one. No, just times 3. This becomes 6.
Cheated? Anybody like to check their answer or no?
6.
6.
Actually, I got 6 over 1.
Hey, that's the same thing as 6.
Yes, it is. I just want to be right. Okay, I'm just kidding. I'm just kidding, guys. All right. Okay, so there we are. So if you initially plugged it in, you got 0 over 0. That is indeterminate. So I took the derivative of the top and the bottom. This part is a little bit tricky, so just remember that the derivative of constant minus 2 is 0. The derivative e to anything should just be itself, e to whatever it was, okay? And then the 2 is a constant that stays there, but then you have to enact the chain rule because 3x could be differentiable on its own, so we take the derivative of 3x, which is just 3. So you have 3 times 2 times e to the 3x power. And you have this statement over here. You plug in 0. So 6 times e to the 3 times 0. That's going to be e to the 0th power, which is just 1. 6 times 1 is equal to 6 divided by 1. Your answer should be 6 over 1. I have one more actually, I don't think I have time. So if you'd like to write this down, this is another problem. You don't have to do this one, okay? But if I have time, I might either continue this next week, L'Hopital's rule. If I have time, I'll make some videos to continue off of L'Hopital's rule. I think it's a little bit better if we do it in class. But this is where we're going to continue off next time we come back, okay? And that'll be class today, right? So thank you guys for coming in. You guys did.
Thank you, Mr. Reed.
Yeah, no problem.
I almost said thank